guys, welcome to Unit 9. First video is going to cover kinetic molecular theory. Now this covers a lot of the theory and concepts that goes into what makes these gas laws work. So you've got 5 parts to this. The first one is gases consist of molecules whose separation is larger than the size of the molecules themselves. But the big part here is that last sentence. Most of the volume of a gas is empty space. That's the big thing. Where these aren't binding together, they're not physically connected, so they can kind of go wherever they want. So when you're looking at a liter of oxygen at a hospital or something, most of that tank is just empty space. There's not a whole lot of molecules in there. Number 2, particles of gas constantly move in straight line paths in random directions. So if we've got our little container here, I don't know why I drew it like a tree, but I will. Let's say this is our molecule. It's going to go straight line, random paths. And say it hits another one right here in the middle. Well, then it's going to deflect in a straight random path, and it's going to keep on going, and it's just a completely random cycle depending on what it collides with, either a container or another molecule. Part 3, gases collide frequently with the side of the container, like we just said, but less frequently with each other. That's because our atom is made up of, our container is made up of mostly space. Kind of the same thing, but puts it into different words. Then all collisions are elastic, which means this big part here, no energy is gained or lost as a result of collisions. Nothing really happens. It's not like a car wreck where your car is going to get squished and you're going to go flying out the windshield. It's no energy is really transferred there. Number 4, particles and gases do not attract or repel. That also means typically they do not bond. Then number 5, the amount of kinetic energy is directly related to temperature. What that means is, down there at the bottom. Meaning that kinetic energy increases, temperature increases. So that means temperature is a measurement of speed. It's just how fast the molecules are going. So the higher the temperature of a gas, the faster those molecules are going. So make sure you understand all that. It'll play a big role in what we do from here on out. So these things describe ideal gases. They react and do things exactly how we predict them. Real gases, like the ones you're actually going to deal with, are gases that act like ideal gases only at normal temperatures and pressures. This last statement is a big one. Low temperatures and low pressure gases behave differently. So make sure you understand that low temps and high pressures, for reasons we'll explain in just a bit, significantly change the way gases react. Because at low temperatures, our gases are moving very, very slow. At high pressures, gas is typically moving fast, and it's colliding with each other more often. So keep that in mind as we go through these. So before we go any further, there's low temperatures, high pressures. Obviously, it's a big deal if we've got 2 giant pictures in there. So now we got to get some definitions. You're going to be seeing a lot of these words a lot throughout the unit, and if you don't understand what they mean, nothing else really makes sense. So the first one, gas. It's a phase of matter. You should know that from Unit 3. Has no definite shape, no definite volume. So if we put a liter of gas into a 10-liter tank, it's now 10 liters of gas. It's no definite volume. If we change the size of that tank, the gas will change the size along with it. Kinetic energy is the energy of motion. You've heard this before. You'll hear it throughout the rest of this year. You'll hear it again next year. It is the energy of motion, whereas potential would be the potential energy. I'm talking about height there. Pressure is a force exerted by a gas on a surface. Great. Partial pressure is the pressure of one gas in a mixture of gases. We'll get more into this in another video when we start talking about Dalton's law of partial pressure, and then that will make a little bit more sense. Then temperature, we always use Kelvin. This might be new to you. You've used Fahrenheit and Celsius before, but now we're going to use Kelvin. It's directly related to the amount of kinetic energy of a substance. Great, that means it's a measurement of speed. And just so you know, 0 degrees Kelvin equals absolute 0. And then STP, this is the big one. Make sure you understand what STP stands for. I'm going to start 4 times because it's that important. If you don't know what STP means, I'll be angry at you when you come in. It stands for standard, temperature, and pressure. You need to know these values. They are on your formula chart, but you're going to use them enough that you need to know what they are. 1 atmosphere is 0 degrees Celsius, which just happens to be 273 degrees Kelvin, is STP. So when you see STP, you're going to need to put in those values. So make sure you know what STP is. Okay, now you get your units. Your units do matter in this unit. You'll use them a lot. It'll help you determine which variable you're placing. Okay, so pressure, we've got three different kinds of pressures. The first one is atmospheres, kilopascals, and millimeters of mercury. You may have seen this before written as torr. That means the same thing. And they will each have different values and different conversion factors. So make sure you're really paying attention to your units of pressure. Volume is normally in liters. Sometimes it's in milliliters. Remember, a milliliter is a cubic centimeter. It's the same thing. They're written down right there. Temperature is in Kelvin, and we'll show you conversions with that. And amount is in those moles that you guys love so much. So now let's do some conversions. Temperature must be in Kelvin for any calculation. Otherwise, it doesn't make any sense whatsoever. Your calculations won't be right. So let's say I'm given 20 degrees Celsius. Well, Kelvin equals degrees Celsius plus 273 degrees. We're not going to give you any Fahrenheits for this class. So we would take our 20 degrees Celsius and add 273 to it. And our new value for our temperature would be 293 Kelvin. Now here's what I was talking about with your pressures in the next one. Your pressures must be the same. You're going to have a starting pressure and an ending pressure. For some reason, you'll get different pressures at the start and at the end. Whatever. You need to be able to convert through it. So if I have 900 millimeters of mercury, and I want to convert that to kilopascals, you're going to have to do that dimensional analysis that we've been doing the last couple of units to figure this out. There's your conversion factors right there. Sorry, I forgot to bring them up. So if we start with 900 millimeters of mercury, this is our conversion factor, 760 millimeters of mercury. And we want to go to kPAs. 760 millimeters of mercury equals 101.3 kPa. And these values are on your formula chart. They're just kind of weird. I'll show you where they are in class. Anyways, you do that math, just like you've been doing for a couple of units now, and you get 120 kilopascals. Okay, so that's all for this one.